And the third talk of this morning will be held online. So let me see.
I think,
Yeah.
So yeah, I'm here. Can everyone hear
By
me?
Jonathan Church. Are you there? Yes.
I'm here. Everyone can hear me?
Yeah.
Can I share my screen? It says you cannot. Oh, I see. I can't share while other people are sharing.
Okay.
There
Please
we go.
share your screen. Let's see.
Everyone
Okay.
sees all that? And you can see my mouse and all that?
Yeah, we can see
Okay.
everything. You can
Okay.
stop. Thank you.
Thank you. Well, thank you for having me here today. My name is Jonathan Church, and I'm a postdoc in Igor Shapiro's lab here at the Hebrew University of Jerusalem. And today I'm going to be talking about some new sampling techniques we implemented into OpenMolcas for generating the initial conditions for dynamics. So today, so here's the outline of my talk for today. The first thing I'll talk about is what molecular dynamics are. I'm sure most people know what those are. And then I'll talk about the initial conditions you need to start molecular dynamics. Then following that, I'll talk about the methodology I implemented into OpenMolcas. And then I'm going to provide like a test example of these different methods on formaldehyde. And then I'll conclude. So molecular dynamics is often performed semi-classically using Newton's equations of motion. So here the force is equal to the negative gradient of the potential, which is equal to mass times acceleration. And you can numerically integrate these and solve for the next step and the next velocity, but you need an initial position and an initial velocity to propagate as a function of time. And so there was already a Python script inside of OpenMolcas, which could generate these initial conditions, and it was found inside the tools, dynamics tools directory. And it was originally implemented by Alessio Valentini. But I implemented 3 new sampling methods into this script, which was normal mode sampling, and then 2 Wigner sampling methods, one based on the ground vibrational state. So if you're just interested in 0-point energy and propagating from that, you would use this one. And then I also implemented Wigner sampling with a temperature dependence. And each of these methods require the normal modes of the molecule. So you have to do a Hessian calculation and then get the vibrational frequencies and eigenvectors from OpenMolcas. So the reason why we originally did this is that there was a little bit of an issue with the old dynamics tools.py script. So here's a trajectory on formaldehyde from the old method. And as you can see, there was a center of mass translation and rotation from those initial conditions, but which come about from converting from normal mode or normal coordinate space into Cartesian coordinate space. And in the new sampling methods, you can see that my methods will actually take all that center of mass translation and rotation out and rescale the energies. So the first thing you have to do to generate these initial conditions is normal mode analysis. And I'm sure most people know what this is, but I'm just going to go over it very briefly. So essentially, you need the Hessian, which is what you get from taking the second derivative of the potential energy surface with respect to the atomic positions. And here's just the generic Hessian, where F is the potential energy surface, and X corresponds to the derivatives with respect to the atomic positions. And for a molecule in the minimum, you would have 3n-5 vibrational frequencies. And for a nonlinear molecule, you would have 3n-6. And here's water. So it has 3 vibrational modes because it has 3 atoms and it's not linear. So the first method I implemented was normal mode sampling, and it's based on a classical distribution. So it treats the normal mode motion classically. And so if you treat the normal mode motion classically, you can solve for the positions and momentum with these cosine and sine terms right here. And the amplitude of the motion is actually determined based on both the frequency of the mode as well as the energy available to that mode. And at time equals 0, these expressions actually simplify here, where it's just the amplitude times cosine and a random phase, or not a random phase, a phase, sorry. And the energy here for the amplitude can actually be determined in several ways. So you can actually take it from a Boltzmann distribution, so classically, or you can also take it from the standard harmonic oscillator energy expression, where you just plug in the quanta of energy you're interested in, and then you can solve for the amplitude. Wigner sampling is not classical, so it actually is a quantum mechanical distribution. And here is the probability for the Wigner distribution for the ground vibrational state. And this is an analytical expression. And effectively at low vibrational frequency or at low vibrational quanta. So here is the position of the normal mode, and here is 10 vibrational quanta, and here is n equals 0, so the ground vibrational state. And as you can see, the classical probability would tell you that you know, the molecule or the mode spends most of its times at the classical turning points because it slows down, stops, turns around, goes back, slows down, stops, turns around, goes back. But a quantum mechanical probability distribution would actually go into the classically forbidden region, and it also just behaves differently. As you can see at the turning points, it doesn't, that's not where it spends most of its time. It spends most of its time around the equilibrium position. So this is important if you're interested in at low temperatures and low vibrational quanta. So the QM distribution, as I said, can extend into classically forbidden regions, and the Wigner distribution satisfies the 3 following conditions. So it satisfies the normalization condition. So if you integrate over all momenta in all positional space, it will give you 1. If you integrate over all momenta, it would actually give you the probability in coordinate space, and if you integrate over the positions, it would give you the probability in momenta space. So now, just very briefly, I'm not going to go into the technical details in the script too much, but I'm just going to kind of give you a brief workflow on how we implemented this. So the first thing, as I said, you need to do is you need to start off with an optimized structure and its vibrational frequencies from the Hessian calculation. And then if you're doing normal mode sampling, you would just select it with -m2. So -m is just the method we're going to select. And so as I said, I kind of generated the energies for this method based on the Boltzmann distribution of energies. And then that would give me my amplitudes, which I can then solve from that t equals 0 expression I showed you a couple slides ago. And then what you need to do is you actually need to convert these normal mode these normal coordinate and momenta into Cartesian coordinates and momenta. And this is actually where the center of mass translation and rotation come from, that spurious thing I showed you at the very beginning. And so you can actually subtract the center of mass motion out, but then you have to rescale both your displacements and your kinetic energies, because when you subtract that motion out, you kind of lower your energy. So you have to go and scale back to what you thought your energy should be. And then once you do that, you can actually take the final values and then go run dynamics with OpenMolcas. And the nice thing about this script is that it will actually give you the correct format for running directly with OpenMolcas. You don't need to do any conversions or anything like that. Yeah, and so the next method I implemented was Wigner sampling, and it's kind of selected, or it's kind of the same thing, and you select it with -m3. So you start off with, again, with your optimized structure and its vibrational frequencies and eigenvectors, and then you sample the momentum and positions independently, and then you plug it in and you solve for the energy from those positions and momentum, and then you solve for the Wigner probability. And if it's greater than a cutoff, then you move forward and convert it into Cartesian coordinates. And then again, you have to rescale it because there's going to be that spurious center of mass translation and rotation, which comes about from doing the coordinate transformation. And then you take them and you go and run dynamics. So and then the last one is Wigner sampling with temperature dependence. Again, it's pretty much the same thing. You sample P and Q independently, and then there's actually this this alpha TF term, which gives you your temperature dependence. And this was actually solved analytically by Wigner back in 1984. And then once you pretty much do the same thing, you calculate the probability from your positions and your momentum, and if it satisfies, if it's greater than a cutoff, then you accept it, you move forward, you convert to Cartesian coordinates, you subtract out the center of mass motion, rescale the energies, or rescale the positions and the momenta, and then you go and run dynamics. So as a test, be showing formaldehyde, as I said at the beginning, and formaldehyde is just a simple 4-atom molecule with 6 normal modes. And here's the energetics using CAS-SCF, 10 electrons and 9 orbitals. And this molecule has actually been really well studied in the literature. So none of this stuff is really a surprise, but this molecule can essentially form CO plus H2 in the ground state, but it has a 90 kcal barrier, as you can see here, which is really, really large. And you're really not gonna probably cross that under normal conditions. So another possible reaction pathway is you can actually excite up to the first excited state, and there's a minimum associated with the first excited state, and this is an end to pi star transition. And then from the Frank-Condon point, you can actually go over the saddle point in S1, and that's an 11.2 kcal barrier, which would then allow you to reach the conical intersection and then go back down to S naught as a hot molecule. And then you can also form CO plus H2 or HCO plus H. So just to show you how each of these sampling methods can yield different distributions, because one's quantum mechanical in nature and the other one's classical in nature. I generated 1,000 initial conditions, and then I just calculated the energetics at time equals 0 relative to the Frank-Condon point I just showed you. And as you can see, here's the Wigner distribution. So I built the distribution in the ground state, I excited it up, and then I calculated the energies relative to the Frank-Condon point. And this is based on the 0-point energy only, no temperature dependence. And then if I do normal mode sampling, which is a classical distribution, you can see that at lower temperatures, the energy is much lower than that of the 0-point energy. And then as you start to raise the temperature, that becomes less of an issue. And then here's the Wigner sampling with temperature dependence. And as you can see, both Wigner sampling with the temperature dependence and normal mode sampling yield very different distributions. And this is important because, as you remember, I said that my barrier was at 11.2 kcals per mole. And as you could see, normal mode sampling and Wigner sampling would predict very different things if you ran dynamics using this system. It would pretty much predict that normal mode sampling would predict that none of your distribution has enough energy to overcome the barrier, whereas in Wigner with a temperature dependence, there's a fraction of the population which can go over the transition state. So just to kind of show you, like actually using dynamics, how it can impact things, I ran 400 trajectories using both Wigner and normal mode sampling at 2000 Kelvin and 3000 Kelvin. And as you can see, at higher temperatures, normal mode sampling and Wigner sampling with a temperature dependence kind of yield the similar distributions. It's not exactly the same, but they're starting to look more and more the same. And that actually makes sense because, as you know, at higher temperatures, quantum mechanical effects aren't going to be very important. And as you can see, plenty of these trajectories should have enough energy to overcome the S1 barrier. And so there were 3 possible outcomes. So there could be no reaction where the molecule just stays on S1 and it doesn't hop down. Also, another possible reaction is that it could form CO plus H2. So here's that video. So it starts off in S1 on the red and it propagates for a while. And then given enough time, it finds the conical intersection and goes off and forms CO plus H2. And then a third possibility is that it forms this HCO plus H. And so as you can see, you know, it's kind of hopping a little bit back and forth. And then finally it forms HCO plus H. And that's the final outcome. And so if you look at the actual distribution from these trajectories, I ran 400 trajectories at the 3000 or at 3000 Kelvin, only about 22 and 18 reacted. So it's really not enough to draw any sort of statistical knowledge in terms of the branching ratios or anything like that in terms of this reaction. But it is enough to show that, like, based on what you choose when you try to build your distribution, you kind of have to be careful and think about what you're doing, because as you can see, each of these methods is kind of yielding different results. And that's all I want to stress. Like at higher temperatures, I think it's less of an issue, but at lower temperatures, and if your barrier is smaller, it can kind of be an issue. So just be careful when generating your distributions. So in conclusion, there were 3 new sampling methods which were put into OpenMolcas, and this is normal mode sampling and also Wigner sampling based on both the vibrational ground state and a Wigner sampling distribution with temperature dependence. And these can be found in the tools, dynamics tools directory. So if you want to run it, you just go look in there for the actual Python script. And each of these methods require a Hessian calculation. So you have to do that with OpenMolcas because it reads the .molden file. And depending on the temperature and vibrational frequencies, as I said, Wigner sampling and normal mode sampling can yield very different results. So you kind of have to be careful with what you're doing. And it can impact things like branching ratios, et cetera. So you could get results that don't necessarily correlate to what's actually happening experimentally. Moving forward, one thing I want to do is I want to methods which can perform normal mode sampling based on vibrational quanta rather than a Boltzmann distribution of energies, because this would allow people to kind of simulate overtone pumping and vibronic coupling and excitations, you could simply model that using this harmonic oscillator energy expression I showed at the beginning. So yeah, because a lot of time people are actually just interested in looking at how a certain vibrational mode impacts a reaction, and this would allow people to kind of study that. I would like to first thank Professor Igor Schapiro, because I've been his postdoc for 2.5 years, and it's really been a pleasure of mine to work for him. I'd also like to thank Alessio Valentini and Luis Frutos, because they were the ones who implemented the original Dynamics tools Python script into OpenMolcas. And I'd also like to thank everyone, both on Zoom and in the audience, for their attention. So thank you.
Thank you, Jonathan. And there is room for a couple of questions. So actually, I have one, which is you show, I mean, the different performances, or not performances, but different results that you can obtain with the different sampling methods. But is there also, I mean, if you really do an experiment, you will find one branching ratio, for example, in your case. So which distribution is best suited? It depends on the problem. It depends on what?
I think it depends on, it definitely depends on the problem and the conditions you're trying to study. So at lower temperatures, I wouldn't really recommend using normal mode sampling, especially because it's a classical distribution where quantum mechanical effects are more important. You probably want to use Wigner sampling. But at higher temperature, as I showed with like the 2000 and 3000 Kelvin results, they start resembling each other. So I don't think it actually makes that much of a difference. And also you're propagating your molecule semi-classically too. So it's kind of, I think the initial condition, even if it has quantum mechanical nature, I think that kind of gets washed out as a function of time. So I would suggest that like lower temperatures, more experimental conditions, like you would probably want to use Wigner sampling, but at higher temperatures, you could probably use normal mode sampling. And also I think normal mode sampling, even though it doesn't perform well at lower temperatures, I think if I implement this sampling based in energy, like in an energy scale rather than in a temperature dependence, I think it would actually be kind of nice because it would allow people to kind of model vibronic coupling, as I said, between like the ground state and excited states. And also you could simulate overtone pumping in the ground state. So I think
the last thing that you show is not doable with the Wigner distribution.
What, can you repeat it one more time? Sorry.
No, so because you said that with the normal mode sampling, you could do these target specific vibronic states. You cannot do that with the Wigner.
No, because Wigner has the ground state, has an analytical expression, and then each excited state also has an expression, but each excited vibronic or vibrational state. I want to be clear, but so it's really not feasible to implement each Wigner expression for each vibrational state. So the thermal Wigner, you kind of lose vibrational information of what state you're actually in. So it kind of so if you want to like simulate like like specific normal or specific quanta and specific modes, you kind of have to use normal mode sampling, I think.
Okay, thank you. There is a question from Roland.
So this requires the computation of the analytical second order derivatives, which is very much expensive.
Yes.
Have you tried, for instance, as a substitute for that, using molecular mechanics normal modes instead?
I haven't personally. Like I literally just I got the project as like, okay, there's an issue with the initial condition generation for OpenMolcas. And he kind of had the script set up to just read the analytical Hessian output from OpenMolcas directly. So I kind of built it from there. That's definitely something we could try to do in the future, I think, just from like an calculation to feed in some maybe not the best vibrational information, but something that's an approximation and see how it impacts the results.
Yeah. Thank you.
Okay. So thank you, Jonathan, again.